Thank you, Nicolas. So, yeah, I hope you all can see my screen. Um, okay, so today I'm gonna talk to you about the TLP technology and what we have done within the AFOSS-DC project that is design, basic design, and also basin test campaign. And yeah, as Nicolas said, I work in France Energy Marine, and I was the project manager during these 3 years for this project. So what are we gonna cover with this presentation? Maybe just shortly, briefly, a presentation of what is France Energy Marine for the ones who don't know us. The TLP concept, maybe you are familiar with that, but I will just give a quick reminder of this technology and the potential advantages for floating offshore substation. Then we will see the design, both specification and the results, the basin test campaigns, and finally the conclusion and the outcomes. So, France Énergie Marine, who are we? So we are the French Research and Innovation Institute. We are dedicated to offshore need, and what we do basically is that we work and we conduct R&D, collaborative R&D projects, and we try to take what the sectors from offshore wind needs and transfer it to the sector through this R&D project. And we are basically divided into 4 departments: wind and ocean dynamics, wildlife and interaction, ecosystem and society, and the last one, the one I'm working in, which is a system and performance. So going to the TLP concept, what is it? I put some picture so you can have a look. Of course, as other type of technology, floater technology, it's coming from oil and gas. So here you can see oil and gas TLP platform. You have a picture of the Bigfoot TLP, which was made by Chevron, and you have here an illustration where you can see the tether. So TLP means tension leg platform, and one of the main difference comparatively to semi-submersible platform is that the kind of mooring lines, which are called tether or tendons, are vertically moored, which means you have permanently a positive buoyancy. And why do we study this? Because there are potential advantages, of course, but also we know that we could have some drawbacks for such technology. The advantages is that because these tethers are permanently are vertically moored and permanently towed, it reduces the vertical movements and maybe also the acceleration, which can be beneficial for both electrical equipment and the cables. However, we also have some drawbacks because again of these tethers, we can have nonlinear effect, which are called springing and ringing. We will come back to that later. That needs to be taken into account. These nonlinear effects are quite challenging to model, and that's also the reason, part of the reason that we have conducted a basin test campaign. And also, and we will not dig so much into this, but the installation might be a bit more complicated than other technology and a bit more complicated, mainly than the installation for semi-submersible. So first, we have started with the design, of course, of the TLP. So what were the design objectives and also the floater specification? First, it was to provide a basic design. We are R&D project, so we don't do detailed design. That's not the purpose, but it's to have a basic design to see if it's feasible. And this basic design was also the starting point for the mock-up to start the model construction for the basin test. And what also, of course, goes with it is to certify the design criteria with a comfortable margin. So as I said, given that we are in early stage and we have, of course, associated hypothesis. So for the environmental conditions, yeah, I might go quick on that because they are the same, mostly the same that what we have taken into account for semi-submersible. So we have considered 3 different water depths. So 400 meter was our base case, but in some case we have considered also 150 meters and 1000 meter water depth. For the wave data, it was exactly the same as for semi-submersible, so 100-year return period wave data. This was in the Atlantic coast. This was a choice because we have considered that the lifetime of such substation, 2 gigawatt substation, would be around 40 years. So that's why we need to consider the long period of long year return period. The same for the wind speed, 100-year return period at 10 meter, and 10-year return period for the surface current speed. And considering these environmental conditions, what were the main design criteria? It was also to adapt to the topside mass and dimensions. It has been presented by Johan, so I will not come back to that. Within the frame of this project, and because a matter of time and resource, and also to ease the comparison, we consider the exact same topside for the 2 technologies. Johan also talked about it, the maximum dimension to ease the construction, and also in some case for the installation. What's one big point? A positive air gap during any life cycle phase, and also to have a keel emergence superior to 3 meter. The stability requirement following the standard, so partly is the same as for semi-sub, the OS 301, but also another which is also a bit specific for TLP. So here I remind the dimension, and of course the maximum acceleration levels you can see here on the bottom right for electrical equipment, and also the maximum horizontal offset for the cable. So here is the results of this design, what we come with, what we came with. So here is the geometry. So to give you some figures, so we stick with symmetrical geometry. So that's why we have this kind of a square shape of TLP to avoid some cross effect. In terms of size, we are around the total size here is more than 80 meter. The column also are quite big. They are a little bit bigger than for the semi-submersible. They are a bit more than 20 meter diameter. And in terms of pontoons, it's also some kind of, as you can see, a square shape, which is a bit more than 10 meter size. Of course, we have also designed preliminary the transition piece. Here you can see, maybe if you remember the figure, but the draft is a little bit higher than the semi-submersible. 26 meter in place and 20 meter towing. And we have also early on estimated the mass both for the transition piece, so around 3,000 tons, for the hull itself, around 13,000 tons, and for the whole thing, with a little bit of ballast for the hull, which is around 18,000 meters. So yeah, that's just a reminder that it's a preliminary design and that it might be optimized later on. We have conducted also some structural studies on the floater and the transition piece, which was a little bit further than what was planned for the submersible. So we consider both static and dynamic structural analysis with some wet mode calculation. Of course, we have looked at the von Mises criteria that have been passed everywhere in the floater and in the transition piece. We have considered, I was talking about dynamic structural analysis, all the modes, dynamic modes up to 100 have been analyzed and have been compared to the topside structural mode, because some structural analysis was conducted as well on the topside. And finally, within the floater inside, we have defined the thickness of the main elements within the floater. The purpose was to have an update for the mass when weight report and to confirm the mass weight. So that's it for the design. So moving on to the TLP basin test campaign, to explain a little bit the objectives and the program, some mock-up design and the instrumentation. So as I was saying, the main objective was to assess whether we have nonlinear effects in the system response in the wave condition considered or not, and to provide different experimental results for this platform concept. We have looked at the tendons tension and the platform motions and acceleration, and to compare the accuracy with the numerical analysis. The free surface elevation, which is particularly important for the air gap, which was quite a sensitive criteria for the design, and again compare it to the numerical model, and to assess the sensitivity of the response to the tendon stiffness. So here I will maybe explain, just to have a look. We have here, you can see some picture. So we have tested 3 different tendons with 3 different stiffness to model 3 different water depths. The scale was 1/50th, sorry, and it was done with a Froude scaling. And you can here see some picture of the test. And so, just to give you an idea, the test program was it was run during 3 weeks. It was done near Brest in Ifremer deepwater basin tests, and we conduct with them over 200 tests, making still water test, pull out and decay, and also regular wave test, irregular wave test, and some specific focused wave test. And we've conducted that with, as you can see here on the right, 2 different orientation, comparing the waves to the floater, 0 degrees and 45 degrees for the waves. Maybe just to give you a little bit more idea, even though I will be quick on that, that's why the experimental design was like this. Of course, we have simplified a little bit the topside, because it was not the purpose of this experiment. We had some calibrated spring and some tendons that were tight from the bottom of the basin using some pulley. And here you can see all the sensors that we have used for sensors, accelerometer sensors, and some wave gauge for the free surface elevation. That's it. Here I can show you a little bit of the results and some picture and hopefully some video. So here it's a kind of storm condition. It's 100-year return period. So you can see that we have model irregular wave with HS around 14 meter and a TP of 17 seconds. So normally you should see the video. So what we have noted among different things is that we still have a positive air gap on this, and that we have only flat motion actually on this test. Here it's basically the same test, actually same wave conditions, but the tendon stiffness are a little bit different, and also the orientation is different. So again, we have maybe some splash, but normally the air gap is positive. And here the difference is you see that we have some visible pitch motion. And finally, I think it's the last video. We have a focused wave, which is sometimes a little bit trickier to realize, to manage in the basin. So we managed to do it. So maybe I will go quick on this slide, but what we analyzed was also the RAO in terms of motion and also after free surface. So we did also, as I think it's quite usual, a calibration work on our model based on those results for the different water depths and for the different incidents. Here also for the different degrees of freedom. So I think that's it for the TLP basin test. To finish with some conclusion and outcomes. So this basic design for the TLP has been successfully done, and all the criteria of design have been met, maybe as you hinted, apart from the one to be constructible within Chantier de l'Atlantique for the floater, but we know that we could build it elsewhere in different shipyards. The basin test campaign have been run, and the RAO after calibration are also in accordance with what has been calculated during the design. And the nonlinear effects have been identified at certain wave conditions, especially focus waves. So what could we do in terms of future work? One step could be to have also some potential updates on the weight estimation, of the top side. If the weight estimation of the top side is updated for different reasons, maybe we change the power, for example, we can of course update the design. We could have also some possible design updates if, for example, the location hypothesis is changed. We will have a different water depth and a different mid-ocean conditions. And finally, we did a long job for the analysis, but we still can continue maybe the analysis of nonlinear effect on the TLP basin test campaign. And also maybe to conclude the part on TLP and semi-submersible. So we have this basic design for the two. They can be compared depending on the sites also and the conditions, the metation conditions, keeping in mind that key aspects are both air gap and acceleration because of electrical equipment. That's it for me. Thank you.